There was a big deal in electric scissors. If you didn't have your scissors, you'd be fired.
Fired over $35. Yeah, that would have fired in her. They tell me that, I just turn and walk out the door.
But if you could stand, after you get past the temporary stage of church systems, they couldn't touch it. The way their manuals are written, it's a union manual without union. Really, if you read it and could throw it back in the face, then you would be No. I got a lot of freedom stuff because I was unsaturated. A year and a half. The only year they ever made one product, I was on their machine, so.
Boards up the ventilation system because the fans are shuts the bathroom down instead of
Oh no, we fixed that. All that stuff got fixed, man.
Oh, sorry. Damn. Thanks. So what I passed back was a quiz for the review that you can work on over the break, because we have a break on Monday. Also passed back what we're going to cover in the class, so you guys will know. Like, for example, yesterday I forgot to assign your homework, but now that you have this, you can do it. Yay! Okay. Do what? This one right here.
So we do this over the weekend?
Oh, that's just for you. You can do it if you want. You don't have to. I'm not going to grade that. I'm not going to grade that review. No, that's just for your own success. That's all your own success if you want to do it. Oh, they're just there. Used to be true, false. Okay, so yeah, for example, let's look at the assignments topic sheet. It says that yesterday we covered 2.2 derived logic, okay? So that means your homework assignment is 2.13, 15, 17, 19, 21, 22. The ones with asterisks are in the back of the book. The answers are in the back of the book. Okay, so today we're going to... today we're going to cover derived... Actually, we're going to cover 2.3, 2.4, DeMorgan's Theorem, and LEDs. So, also that's your reading assignment. Yeah, that's the way it works. That's the way the form works. You just look at the section. You always have a reading assignment before we lecture, and then you have homework after we lecture. So that's the way I do the class. So, if we're done, for example, with DeMorgan's Theorem today, that means for next time you need to read 2.5, 2.6, enable an IC gate. So just always read before we come to lecture, and then the homework is after. Okay. And this is posted on Moodle. I put it under homeworks and assignments, so I probably need to check it just to make sure that it's 100% up to date, but it's mostly up to date. And I guess I need to take the roll really quick so we can get started with the lecture. Okay, Corey? Benjamin? Oh, you have homework? I don't think we had homework yesterday, did we? Oh, we had homework from last... That's right, we did have homework. I was thinking about yesterday's lab. Sorry about that, guys. Yeah. Okay. Okay. How'd you do on that?
this, once I realized what they was asking me, I was no problem.
Okay.
Because I was actually visualizing the point of
Okay. Okay. Okay.
About the logic highs and lows, you said it like that. Like this.
Okay.
Truly right?
We'll go over it. I'll go over
Yeah,
it.
yeah. So I think it's this one.
Yeah. Benjamin, you have homework 2.1 through what? 2.9. Okay. James. You have any problems with it? No. You think it's good? Okay. Dakota.
Yes.
You have it?
.1, 2.7, 2.9.
Okay, thanks. Jesse. You have homework?
What's these asterisks mean on this sheet?
That the answers are in the back of the book. Santuan? Christopher? Have homework? Oh, okay.
So 2.4 on that side, the rest over there.
Any problems?
No.
Okay, good. Leon?
It's here, but I started over here to do it a little later.
Did you have any problems with those homework? No, it's pretty simple. Okay. Jason?
That's notes from all the reading and stuff.
Oh, you didn't do the assignment?
No, I can. Oh, tonight.
Okay, you have the
Is that
notes.
okay?
Okay. Okay, yeah,
I'm sorry.
it's okay. Austin? Not here. Sometimes I can't see over those screens. Okay. Gary? Homework? Okay. Lucas?
I forgot my examples, so just redid them real quick. Just earlier. I did them better.
You did those?
Tell them, yeah.
Okay.
I did them better.
Okay. Okay. Don? Okay. Kevin? Kevin, other guy. Okay. Any problems? Any difficulties? Okay. Thanks. Tyler? You didn't do your homework? Okay. Clarence?
Starts down.
Okay. All right. Okay, I'll post these solutions on Moodle for you guys. Is there any... I can maybe do one problem. Is there any one problem that's just really struggle with that I need to do right now in class? Okay.
You could do the 2.3 and 3 answer, I guess.
The 2.3.
It's a 3 input.
2.3. We only had problems 2.1
All of
through
between 2.1 and 2.9 is what you're going to
That's
lose.
different.
Oh, 2.3. I see what you're saying. 2.3. Oh, do 2.3. Okay. I can do that one. Okay. Digital. Oh, no one can see what I'm seeing. Because I gotta switch this. Yeah, there we go. I'm just gonna put it up on here because it's probably easier. Okay. I have to draw it. 2.3. Can you read the problem? This question. I don't have my book with me. Can you read the problem statement for 2.3? Leon, somebody. So draw the symbol for 3-input OR gate and the rectangular. Okay. So that's the solution right here. Is that good? It's the arc, the 3 arcs with the inputs A, B, C, and then this one is the square, 3 inputs. Okay. Anything else for this one? 2.8. 2 point. Any more odd ones? Because I have the odd ones. 2.9. There's 2.7. If you guys were wondering about that one, switches must be connected in parallel, and then this one looks like that. 2.9. 2.9. Okay. And we'll jump down to the even ones now. Jump down to the even ones. There we go. So 2.6, that one was, the switches would be seriesed. 2.2, symbol of an AND gate. 2.4, everything is a 0 except for we have 1, 1. 2.8 is 2 cascaded AND gates. And that's it. Alright. Covered everything on the homework? Okay. Good. Yeah.
I'd ask for the symbol, the equations,
No, when that's for the symbol, you don't have to draw the equation. I'll ask you for the Boolean expression if I want that. Okay, so we're ready to go. Okay, so today we're going to talk about section 2.3, DeMorgan's theorems. DeMorgan's theorems are used to convert from one type of gate to another. Really, it's for the situation where when you're doing discrete logic, when you're using the dip packages, and you have one extra gate package left over, and you don't want to go use another gate package. For example, if you have an AND gate, and you don't want to go grab another OR gate package because it's going to take up another entire package space on your board, you you have these extra gates that you could use for something else. So you can make an AND gate out of an OR gate if you have some inverters and things like that. So it's also useful just when you're doing basic digital design. It's useful to be able to have these theorems. So a NAND gate can be represented by an AND gate with inverted output, and a NAND gate can be represented by an OR gate with inverted inputs. So a pictorial diagram for DeMorgan's theorem is as you can see on the screen. You can say that this circuit is equivalent to this circuit. Now, the easiest way to remember this for me, this is what I do, is I say, and it doesn't really matter what the gate looks like. I mean, this could be an AND gate, doesn't matter. It could be an OR gate. DeMorgan's theorem basically says you change everything about that gate and then it's equivalent. So what that means is if I notice that the inputs A and B, they do not have bubbles on them, right? Okay. Now, so if I put a bubble, I change those to bubbles, and then change the gate from an AND to an OR, and then on the output, this one has a bubble, and so on this one we're going to remove the bubble. Then what we can say is that these two are equivalent from the standpoint that if you put a 1 and a 1 on A and B, and a 1 and 1 on the A and B of this gate, you will get this exact same output, which would be a 0. And in fact, no matter what combination of A and B you put on the input of the first, the second will behave exactly the same. So that's DeMorgan's theorem. And you can also write this with an equation, and you can see that the equation form is right here. So A dot B bar is equal to A bar plus B bar, or A naught plus B naught. And it works both ways, like I alluded to before. A NOR gate can be represented by an OR gate with inverted output. A NOR gate can be represented by an AND gate with inverted inputs. Okay. So that means you can change. The implications are that you can change an AND function to an OR function, and you can change an OR function to an AND function. So you just invert the inputs and outputs and change the gate. So from a Boolean expression standpoint, you can think of it as the equation that you see on the screen. So A dot B naught is equal to A naught plus B naught. And really, if you think about this equation, the easy way to memorize it is, it doesn't really matter what equation you could write. For example, this is one of the equations that he gives, but I could write A dot B. Okay, what would be the DeMorgan's equivalent of that? Well, I have to change everything about the equation. First off, I have to invert the input. The way that I invert the inputs would be, I do A naught. I also have to change the dot to a plus. I change the B to a bar over that. And then I have to change the output by inverting the entire thing. So that's DeMorgan's theorem as well. You can create your own DeMorgan's theorem. It just simply says you change. The way I interpret it is, I've never been told this through a book, but this is the way I think of it, is you change everything about that expression. Easiest way to do it. And again, I don't memorize this equation. I don't memorize this equation. What I memorize is you change everything. It's simple, right? It looks really confusing and complex if you don't think of it like that. If you go ahead and try to memorize these equations, it's going to be difficult for you. So the following are two common errors associated with DeMorgan's theorem. So what's the problem with those two?
They didn't change the sign. Plus sign. Multiplication sign.
They didn't change the, oh yeah, you're right. Yeah, they didn't change the plus sign. So on this equation, they inverted A and B, so that's good. They inverted A and B. But what about the dot in the middle? They forgot to change that, right? What else? That's really all they forgot, because they remembered to get rid of the bar across the top. The bar across the top changes the output. That's equivalent to the little bubble at the output. Okay, so what about this one, the second one? Same thing. Yeah, you're right. Same thing. Okay.
That's what it is, bar across both of them.
The bar across the top, across everything, that's equivalent to the bubble at the output. Active logic levels. Any input or output that has a bubble is considered an active low. Yeah, that's true. I agree with that. Any input or output that has no bubble is considered to be active high. That's true. So this is a statement about active low. We already talked about active low logic levels. He's just restating, making a point that, like a NAND gate. A NAND gate has a bubble on the output. So that's considered active low logic. Yeah. So this would be considered active low because of the bubble. Active logic levels, nor at least one input high makes the output low. All inputs low make the output high. Okay? So you can see here we have a equivalency. This is DeMorgan's theorem in practice. So if you take a NOR gate, then it will be equivalent to, we call this a bubbled, I think most people call it a bubbled AND. Okay, bubbled AND. When you say bubbled and then the word AND or whatever, you're talking about bubbled on the input. If I wanted to say that there's a bubble on the output, I wouldn't say bubble on the output, I would say NAND. You see? So bubbled AND would be, would be this. And a bubbled NAND would be same thing with a bubble on the output.
So it's double inversion, so it would make it a positive instead of an invert.
What's that?
Wouldn't that be a regular AND gate by the end?
Nope. This actually is a regular OR gate. And that's, a lot of people don't teach it that way, but I think of it like that. I think of it like, let me push this button for a minute. Okay. Get that little thing. Erase all strokes. Okay. One way I think of DeMorgan's theorem is like this. A bubbled NAND gate is equal to an OR gate. Okay? a bubbled NAND gate. That means if you have a bubbles on the inputs, a bubbles on the output, it's equal to its opposite function. You know, ORs and ANDs are considered opposites of each other. So it's equivalent to an OR. So a bubbled NAND is equivalent to an OR, and similarly, a bubbled OR, or NOR that is, bubbled NOR, is equal to an AND by application of DeMorgan. This is directly comes out of DeMorgan's theorem, right? Because look, the bubbled NOR, you change everything about that bubbled NOR, and you wind up with the AND, right? Okay. So that's the best way to think about it. So how do I get rid of this pattern thing here? Oh, cancel. No. I got into this drawing mode, and I don't know how to get out of it. Let's see. Sorry guys, I shouldn't have went to a feature that I didn't know how to get out of. I'll just keep hitting undo until it goes back, maybe. Yeah, it didn't work. Oh, there we go. Okay, had to exit from the drawing. I used this thing a lot last semester, but I haven't used it this semester, so I forgot how to use it. Okay. Okay, so that's really it. I mean, that's the concept. And so now we have homework problems that I've assigned. Or actually, it's going to be, I'll show you what the homework problems are in the end of the section, but they're also in the handout that I gave you. Now, we've already talked a little about LEDs and switches, and I wish I would have went over these slides during the lab, but I just forgot that these slides existed, actually. So we've already been using logic switches, and we used to use those red trainers in the back that have the logic switches integrated inside of them, but students didn't understand how to use a switch or how to wire one up, so I got rid of those. I put those in the back. But if you do some tutoring, the tutor did say that he would like to use those just to make it easier, so we may bring a couple of those back out. But I think it's good that you guys know how to wire a switch, because when you do something like a real project, you're going to have to know how to do it. So the common types of switches, you have push buttons, normally closed, single pole, single throw, single pole, double throw. Now, for a switch, I think you guys understand this because I already did the lab, but the way a switch works is, the easiest way to think about it is, think about the switch not being there at all, okay? You have an input to a gate. It could be any gate. And to pull it up to 5 volts is considered high. To pull it down to ground is considered low. Okay? So somehow we have to convey that voltage to the input of the gate. One of the simplest ways to do that is, for example, one of the simplest ways to pull a signal high is just connect it directly to 5 volts. Right? Or you can connect it directly to ground. Now you could do that, actually you could do that with, let's say, let me draw a circuit right here. Let me take a switch, and I have another switch, and I have a switch. So this is, what type of switch is this? Does anybody know what type of switch this is?
Single pole, double throw.
Yeah. Single pole double throw switch. So what we could do is we could come in and we could say, okay, we're going to tie this to 5 volts. We're going to tie this to ground. When the switch is in the up position, the input to this gate is going to be logic what? logic high, which is logic 1 level, and when it switches to the bottom position, it's going to be what? 0. Does everyone understand that? Is that easy to see? Okay. So that'll work as a switch. It's not as common because single pole, single throw switches are just more common, I guess. Really. They've only got 2 terminals. But I guess they're cheaper and they're more common, especially for a push button switch. Normally a push button switch it's a single pole, single throw. It's just easy. Mechanically and construction wise, it's easier too, right? So how are we going to get this function into a single pole, single throw switch? Well, I'll tell you what we can't do. What we can't do is if this is our input here, we can't take this and wire it high and then come in here and put a switch here to ground. Because what would happen when you close the switch?
It's short. You're going to zap whatever power supply you got.
Yeah, you're going to have like 100 amps going through here or whatever. According to Ohm's Law, it's going to be I equals 5 volts over your resistance. The only thing you have is the resistance of the wire, which is really low. So if you do this equation, anytime you have a 0, anywhere close to 0 on the bottom, this tends to go to infinity. Just do it with your calculator. Put any number in on the top, 5 volts, divide by some really 0.0001 or something like that. It's going to be 1,000 or 5,000. 0.0001, yeah. So that would be 1 milliohm. 5 divided by 0.001 would be 5,000 amps. So it's not going to work. So what can we do to make this still work? Well, what we can do is we can put a current limiting resistor right there. So the current limiting resistor will still pull this node up high. It'll just do it slower, which is okay. We don't care about that. Because we're talking about seconds and things, so we don't care that it goes up in 1 microsecond. It's still fast. So now the equation for the current through this part will be I equals V over R is 5 volts over, if you have a 1K resistor, you got 1K. So now what's your current going to be? 5 milliamps. Yeah. Definition of milli is what? 1,000th. So this part of the equation, this part of the equation, 1 over 1,000 is the definition of milli. So it's going to be 5 milli. So that's the way it works. I know for a lot of students it's confusing. But once you get used to doing it, then it's not that difficult. And what you get with this is the waveform that you see on the screen. You can, by pushing the switch, when you push the switch, you actually get the 0. You get when the switch is closed, you get a low logic level. Now the question is, can you reverse these components and still get the same thing? What would you get if you reverse the components?
If you reverse it, yeah, you get a short.
If you reverse the components?
Swapped out the switch and the receptor and
Yep.
resistor.
Yeah.
Get a short to ground.
Oh, yeah, it'd be inverted. Just be inverted.
The waveform would be inverted?
The input.
Yeah,
Yeah.
Because when the switch is open, you have 0 going to the
Yeah.
circuit.
Yeah, so what would happen would be, well, it would look like this. So it would be the opposite. When the switch was open, you would have ground. Yeah. When the switch was open, you'd have ground. When it was closed, it would pull it high. And you can do that. Most people pull the input high with the resistor, and then they ground it with the switch.
Is there a reason for that?
I was just trying to think of a reason before I told you that, but I couldn't think of a reason.
You still have to put a resistor in there to limit the current or whatever. Right.
Resistor limits current to a certain.
I think either one's just as fine, but it's just, I don't really know if there's a reason why people do that more. But I will tell you that this as it's written here, this would be considered like a kind of an active low switch, because when you push it, it's going low. So it's what we would call that active low switch. Because in your design you would have to say, okay, low is on or true or activated. So if you wanted to get an active high switch, you'd invert those functions.
You're saying that, is that going to be on the side of the microprocessor? Is going to be defining that as...
Yeah, like in the microprocessor, if it went to microprocessor, you'd have to say, when high, don't do anything. When low, do this. Yeah. Yeah. So you could have the inverse function inside your microprocessor code or in your digital logic or whatever.
Like if you had it reversed and went the way we were talking about, you have the switch and the resistor reversed. Is there a way that it can send too much signal to the switch? To the chip?
Too much signal? Too much current?
Yeah, that's what I meant to say. Too much current.
Well, it doesn't send it to the chip. It actually will bypass the chip. Yeah, if you do have too low, the only way you can mess this up is if you choose too low of a resistor.
Okay, right.
Another way you can mess this up is if you don't tie these two rails. If this digital circuit has to be VCC, these have to be the same voltage level. You can really mess your circuit up if you have those connected to different levels. Like let's say you have over here a 5-volt regulator, and then you have a power supply over on this side, and it's maybe 5.2. Over here you have 5. Okay. Well, now you could turn on it. You could start to turn on an ESD protection diode inside of this circuitry. They need to be at the same level. It's kind of beyond the scope of this class to talk about that, but it has to do with ESD protection diodes. They're inside every chip, and you can turn those on. It doesn't expect to have a logic input voltage higher than its rail. It's logic.
You can have one slightly lower or higher.
It may not detect it, but it's not going to hurt. It's not going to hurt the circuit. It's not going to destroy the circuit. You can actually destroy the circuit by having the input voltage too high. You're not going to destroy it by having the input voltage too low. But by having the input voltage too low, you may not be able to detect that it's actually high. So, yeah.
By moving the resistor, you're changing that resistor, you're putting it, right now it's in series with the digital circuit. If you put it the other way, it'll be in parallel, so you're going to change the overall resistance of the digital circuit. Pretty drastic, probably.
No, I mean, this is, yeah, you're not going to, it's not going to change
On the
anything.
other side of the digital circuit is ground. If you put VCC in between the resistor going to ground one way and the digital circuit going to ground the other way, now they're in parallel, so you're going to have...
I mean, you talking about reversing the components? Is that what you're talking about?
Yeah, you're going to have the reciprocal of the resistance.
Okay, let's draw it really quick and see what we've got. So let's say that we put a switch here, and then we put this side to ground, Okay, put that to ground. And this is 5 volts. Okay, what you would have is you would have, when the switch is open, you would have this input grounded. Is there any problem with having the input grounded through a resistor? No. There's no problem. Now, if we move the switch and close the switch, now you're going to have 5 volts at the input to this digital circuit. And you're going to have current flow like that. It's going to go through the switch, through the resistor to ground. Is there any problem with 5 volts being at the input of a digital circuit if the digital circuit itself is connected to 5 volts? No. So there's no problem with the circuit.
What I'm saying is, the way it is on the board right there, the resistance of the digital circuit and the resistor are now in series with each other. Right?
So will it go?
So the current is going to be low through those. Because
You're saying that this is in series with this?
No, the original drawing.
This drawing?
Yeah, when it's high, the resistor is in series with the digital circuit.
In series. I don't really agree with that.
It's not.
The digital circuit has VCC here, and it has ground right here.
Right.
And it has inputs. I wouldn't really say that it would be in series.
There's a current flow from VCC through the resistor into the digital circuit to ground, right?
Yeah, but this circuitry here is not really setting up the current through here. The current through the digital circuit, it has its own. It's a capacitive input. So there's really very little, almost no current flow into the chip for a CMOS chip. For a TTL chip, there would be some current flow, but the current flow is only going to depend on Ohm's Law, which would say if there is an internal resistance, it would just be whatever I would be V over R. So whatever this voltage is on this node, current's going to flow. So it doesn't really matter whether this circuit is in series or parallel in that case.
The internal resistance is so high it's negligible.
The main difference between the two circuits from that aspect would be this circuit, there would be some delay time, there would be some rise time on the signal going high. In other words, it would be like that. But whereas when you connect the switch to ground, it would instantly fall. In the other circuit, you would have the opposite effect. It would go high instantly, and it would fall slowly if you switch the elements. Because on one side you're going through a resistor, the other side you're going through 0 ohms. And really this input has a certain capacitance, this charge to. And so really what you're doing is you're charging or discharging a capacitor, either through a resistor or through a switch. And so charging it through a resistor would have a delayed effect. It would go slowly. And connecting it to ground directly through a switch that has low impedance would instantly cause it to drop. In the other circuit, if you switch the elements, it would look like this. So they're not the same, but they're equivalent. I wouldn't worry about it too much. Either one you want to do would be fine, I think. So, okay. Oh, it's kind of hard to see that one. But hopefully you guys can see that. In this one, you can see that you have a push button switch and you're pulling this high. Same circuit. Now when you push the switch, then you're connecting it to ground and you're going to get the same function. When the button is pushed, you're going to have a low. So it's going to be an active low switch. Or if you wanted to get, using the same pull-up resistor methodology, which is common, you could use a normally closed switch. And in that case, when you push the button, it would open and then you would get what we would consider an active high function for your switch. Now, if you had a two-position push-button switch, then you could You could have two different signals if you wanted, and you would get this action. I don't really know why you would do that, but so a two-pole push-button switch allows for normally high and normally low levels from the same switch. And again, I don't know why you would want that. I've never actually seen that or know what the usefulness of that is. So we talked about inputs to the digital logic, switches and resistors. Now we've been using a simple output. One of the most basic is a light, a lamp, or a LED, used to indicate the status of something. For example, my guitar amplifier that I built, I used an LED to indicate, whether the switch was on, so that you don't drain your battery. So you know to turn the switch off. That's a very simple application. You could make that more advanced, and you could put some circuitry inside of the guitar amplifier preamplifier to say, if the battery gets below a certain voltage, make the LED blink, or turn the LED off, or change the LED from from green to red, because they got those tricolor LEDs that they'll go 3 different colors with one LED. So that's what I want to do next on the guitar amplifier. I want to have a battery monitor circuit. Basically, what you could do is just when the voltage of the battery got to a certain threshold, you could have a comparator and cause your switch to go from green to red, or from green to yellow if there's a warning, and then if it really gets low, you could go to red. So, because it's kind of important when you're playing music to know that you got a good battery. So used to indicate the status of a digital output. You can use it for analog. The voltage across the LED is normally between 1.5 and 2.3, 2.5 volts. And the diodes have to have a current limiting resistor. So the symbol of the LED is a triangle with a negative slash. I think of it as a negative sign. The reason I think of it as a negative sign is because it helps me to connect it. The negative sign goes to minus voltage, and the opposite side goes to plus voltage. Okay. So the voltage across this diode is going to be, you could say about 2 volts, 1.5 to 2.5, so approximately 2 volts. And yes, we call the one side the anode, and we call the other side the cathode. And by definition, anode, the way it was originally defined, anode is whatever terminal the current is entering. The current is entering into a terminal is considered the anode. Okay. Same is true with the battery. So with the battery, the actual anode of a battery actually changes depending on whether you're using it to supply current or charging it. So the anode can switch in a battery. But in this device, current will only flow in this one direction. It's a single direction, a unidirectional. It's kind of like an anti-siphon valve for landscaping. It only lets the water or current flow in one direction, and will not let the current flow in the other direction. So if you connect these backwards, then you don't get anything. You don't get the lamp glowing. You're not going to blow anything up, but the only way you can blow something up is if you forget to put a current limiting resistor, because these themselves are almost like a wire. There's really almost no current limiting in the diode itself. It's just almost like a wire that has a given voltage drop across that wire. Sorry about that. Yeah, it's time for us to go. So let me just go through these really quick. That's what they look like. They used to provide a visual indication of a logic state. Simple circuit. You have a battery, resistor, and a diode. You have to have it in the right direction. And the proper direction is the plus terminal. You have to have a resistor, and the plus side goes through the side that's opposite of the minus. Okay? So into the arrow. So the current flows in the direction of the arrow. That's the easy way to remember it. Now the lower the resistor, the brighter the LED. Okay? But the more current you're going to draw. And the quicker you're going to diminish your battery. So for my guitar amplifier, I wanted the LED to light as little as what I could distinguish that it was on. And maybe a little bit higher than that. But I basically designed it so that it could run for like I can't remember, I think it was 2 full days continuously, which would wind up being that, because I only use it maybe an hour or 2 at a time, so that would last a long time. Design it to operate for 2 full days straight. And so you can set that current by changing that resistor. You can set that. And you can look up the capacity of the battery, and you can determine how long you want your battery to last. Yeah. So you guys can look at these slides. Here's an active high, active low output. This is something we should at least discuss a little bit, because a lot of chips will use this circuit. They like to pull the diode high, and they like to use the output of the digital logic to either ground or pull it high. So it kind of looks like it's in the opposite direction. Whereas you would think this would be making more sense to just drive the LED from the top through a resistor. And there is a reason why they do that, and that's because usually the sinking current for a device is higher than a sourcing current for a device. And we do have the rocket meeting right now. So anyone that wants to be part of the rocket meeting, let's go down. But make sure you do the homework assignment right here. This is the homework assignment for this section. And that's going to be on Moodle.
Is it on the handout?
Yeah, it's on the handout.
So there's
Yeah. In my office.
or wherever I can put it, just sort of be safe.
Where are you going?
With you?
Oh, you're going to go with me? You don't want to take it with you?
Well, I guess I could take it with me. It don't matter anyway.
Yeah.
If you prefer me to take it with me, I will.
Yeah, let's just take it.
All right.
Yeah.
Is this Keynote on Moodle also? Moodle?
What's that?
Is this Keynote on Moodle
Keynote?
or whatever this is?
What is this? Keynote.
Not the assignment, but like all the.
All the PowerPoints. Okay. Yeah, I usually put these on Moodle. They're not on there right now, but I usually upload them after I do the lecture.
Yeah, because
Yeah.
I was trying to write some of it and you was going.
Too fast. Yeah, they're going to be on Moodle. Yeah, all the slides are on
I gotta
Moodle.
write real slow so I can read my handwriting sometimes.
Yeah,
Don't forget to announce the rocket.
we did. I did already. Yeah, I
Yeah, they're
think
meeting right now if y'all want to go over there some days.
Yeah, where's it located? Classroom?
Drafting lab. next
right
door.
over there.
Doing good?
Yeah, I'm headed over. I think it'll be. Okay. I'm probably just going to leave my laptop set up in here.
So if you don't, I'd lock the door. I thought if you switch to LED, reverse, it would like detect light. Was that just kind of like
Yeah.
an LED? Yeah.
It detects light.
So how's it go through the diode part of it then? If you go under one direction, to be able to detect if there was a connection.
It actually goes the opposite
It
direction.
still goes the opposite direction. It still goes.
When you use a LED as a source,
Yeah.
it goes out.
It's
It's kind of
I was trying to figure out like it's like
Am
another
I?
diode.
Yeah.
It's like a wall. Flip it. It still detects something. I don't know.
I'm going to lock the doors. So. Yeah, I'm going to lock the doors.
It's 138.
Right.
I mean, you guys can stand here if you want, but I'm going to lock the door from the outside just so someone new.
Yeah. We'll see what it's about anyway.
That's gonna be too much. Gonna be too much. I already got enough on my plate.
Yeah. Just kind of interesting.
It just seems interesting. Way too much.